Hello, in this lecture, we are going to discuss a few concepts regarding electrostatics, and in electrostatics in particular, we are going to do some problems which would involve Dirac Delta Function. Okay, so the title of the topic is mostly electrostatics only. So mostly we are going to do today electrostatics, and we are going to see how you can expect your Dirac Delta Function to come to play an important role while describing certain problems. Okay, so this is what we are going to do. So let us not waste our time. Let us start revising what we've done in Dirac Delta Function. So we know that what is Dirac Delta Function. So Dirac Delta Function represents models, or it represents your point charge density. So you know that whenever you have a point charge, let's say you have a point charge centered at 0. So how to describe the volume charge density of such a point charge? So natural question arises is how to describe the volume charge density of a point charge. Okay, now because the point charge is something which will not have a dimension for point charge. So you know that your point charge will not have a dimension. So when it does not have a dimension, how can you define something like dq upon d rho? Or you can say q upon rho, q upon v, where volume is almost 0. It's actually not even tending to 0, it's actually 0. So you do not have any such function which can define a volume charge density of a point charge. So in whatever calculus you know till now, you cannot have one cannot describe you can say volume density of point charge. One cannot describe the volume density of a point charge. Why? Because you know, if you have this volume charge density, then you have some dq divided by dv. But now, if your point charge is there, so you have some q or v, and v is exactly 0. And you do not have such things in your calculus which says that even if you divide by 0, it can represent you something physically significant. Okay. So how did we do? Or in Dirac Delta Function itself, we know we've taken a class and we've done this thing, that in order to describe the volume charge density of a point charge, so in order to define the volume charge density of a point charge, you would require something called as Dirac Delta Function. Okay, this is something that we've done already. So in order to define the volume charge density for point charge or point mass, all these things would require a Dirac Delta Function. So one of the implications from where you can have some sort of motivation regarding Dirac Delta Function is the volume densities of point charges and point masses. So in all of these cases, you can expect volume charge density. You can expect Dirac Delta Function to take a significant role. Okay. Now in this regard, let us do a few problems and go ahead. Okay. See. So if I want to write a few things, like a few things that I'm going to tell. If I want to write the charge densities of the following, how would I write charge densities of the following? So for example, if I want to write my point charge q, if I want to write my charge density of the following, means what? Point charge, not point charge, in fact, we will say q, charge q, distributed uniformly over the sphere of radius r. So if my charge Q is uniformly distributed over a sphere of radius R, and if I want to write the charge density of this particular charge Q, which is distributed uniformly over the sphere of radius R, what should I do? And I should know that because of the symmetry of the situation, I should prefer using spherical coordinate system. I should prefer using spherical coordinate system. So what I would do is, I would simply, okay, now it is quite clear to you that if I want to make a, let's say, if I want to, so whatever charge is located, it is, so whatever charge is located, it is located on the radius, right? So let's say the radius of the sphere given is capital R. So entirely your charge is located on the sphere, and this entire charge is uniformly distributed. So total charge is capital Q, and it is distributed entirely on the sphere of radius capital R. So on the entire sphere, you can say your total charge is capital Q, and it is uniformly distributed. Okay, it is uniformly distributed. Okay, so if it is uniformly distributed, the entire charge, since it lies on this thing, so what I would say that my charge density would look like this. So R will be function of some, rho would be some function of R theta and phi, because now it would be quite apt to use your spherical coordinate system, because I have this charge distributed uniformly on the over the sphere of radius R. So the symmetry of the problem itself suggests that I should use a spherical coordinate system. So there would be some constant. I don't know what it would be. And certainly, since my entire charge is located on the sphere, so it suggests me that entire charge will be on the capital R. So if I take capital R plus, there would be no charge. If I take R minus, there would be no charge. So this certainly describes my situation quite clearly, although I'm not aware what my A would be. That I would find, no doubt. Is that clear to you? So what we are doing, we are trying to write some charge distributions. So we were doing electrostatics, and I told you that while doing electrostatics, how important is your Dirac Delta function? That is what I'm trying to tell. So in Dirac Delta function, in the classes of Dirac Delta function, we've come to know that if we want to describe a volume charge density of a point charge, we are left with no other option than to use the Dirac Delta function. Okay. Now I'm doing a few problems. Let's say if I want to write the charge density of the following. First one is, let's say if my charge Q is uniformly distributed on the sphere. So uniform distribution means whether you write dq upon dv or you write q upon v, that happens to be 4 upon pi r square, they're one and the same thing. So basically what does it mean? It means that equal volume would contain equal amount of charges. So like in every dv element, you can expect this dq. Okay, there would be no such disparity between this thing. So equal differential volume would contain equal differential charge. So this is how it is defined. So this is a uniformly distributed charge Q over the square of radius R. So what I did, I'm just trying to write the charge distribution of the following. So if I want to write the charge distribution of the following, I know one thing. One thing is for sure, that since my charge is located entirely on the sphere surface, what does it imply? It implies my entire charge would be like if I take R plus, there would be no charge. If I take R minus, there would be no charge. My entire charge is on R. So it implies that I can specify my Dirac Delta function this way, and there would be some constant. I'm not aware about it, but I will find it. Is that clear to you, both Kalpana and Bharat?
Yes, sir.
Okay. Now, if I want to find this A, how should I find this A? So I already know that my rho d tau, when I integrate it, I will get capital Q, isn't it? So rho d tau, when I integrate it, so it will give me integral. And you know that in spherical polar coordinate systems, I'm writing this r theta comma phi. I will write r square. I will write sine theta. I will write d theta. I will write d phi, and then I will write d r. Yeah. For the full sphere, my r would be from 0 to capital R. Theta would lie from 0 to pi, and phi would lie from 0 to 2 pi. Is that clear? So this will give me capital Q. So if I integrate it all over, what I will get? So I know that this rho is given by, don't take this A. So rho is given by what? Rho is given by A times Dirac of R. So I'll write A outside. Integral this particular thing, because my rho is dependent upon R only. So all these things will give me 4 pi. Don't worry about it. So I will get integral from 0 to capital R. And here I will write, I think, Dirac of R minus capital R. And then I should have a R square, and I should have a dr. And this entire thing will give me Q. Is that clear to you? So what it will give me, eventually I would get Q upon 4 pi A, and this particular thing would be what? So it is R square here. This is centered at R. So filtering property gives me that this would be equals to what? This will be equals to R square is equal to A. So A would be equals to what? Q upon, A would be equals to what? So Q upon 4 pi R square. So A would be equals to Q. So my volume charge density, I can write Q upon 4 pi R square Dirac of R minus capital. And that indeed should be the case. I know that my volume charge density is Q upon 4 pi R square. But what about the presence? The entire volume charge density is present on the sphere, on the surface of the sphere. So this should come ideally. So ideally, this would be a volume charge density. Is that clear to you?
So this delta R minus R represent infinite delta functions on R radius, right?
Yeah. It implies that your entire distribution is at R only. Okay. And if you integrate it all together back, you will get this Q. So you can get Q. So till now in the standard 12, till standard 12, you've done this, that if I want to write the rho, it will be Q upon 4 pi R square. But better way of writing the charge density would be this.
Yes, sir.
Is that clear? Okay.
Yes.
It represents that whatever charge is there, it is on capital R only. Charge density is there, that is on the capital R only. If you take R equals to, let's say, R plus H, then there is no charge density, isn't it? If you take R minus H, there would be no charge density. So entire charge is on the sphere itself. So it represents that, and density is given by Q upon 4 pi R square. If you integrate it all together, you will get the answer as Q only. So this is quite right. Is that clear?
Yes.
Okay. Now the same thing if I ask for the, let's say, in cylindrical coordinate system. So let's say in I should write what? Let's say in cylindrical coordinate system. So in cylindrical coordinate system, if I have this, let's say not defined charge, but define a charge per unit length. Per unit.
फिर उस चार्ज डिस्ट्रीब्यूशन का हम ग्राफ ड्रॉ कर सकते हैं?
चार्ज डिस्ट्रीब्यूशन का ग्राफ नहीं ड्रॉ कर पाओगे, बिकॉज यू सी
वो 3D में होगा।
हाँ, यहाँ पे इन्फिनिट हो जाएगा। आर यू गेटिंग द पॉइंट? सो बेसिकली हो क्या रहा है, तुम्हारा जितना भी चार्ज डिस्ट्रीब्यूशन है वो सारा का सारा किस पर है? एक यूनिफॉर्म रेडियस के सरफेस पे तो है। सो इट इज जस्ट लाइक अ पॉइंट थिंग। सो अगर तुम चार्ज रो लिखोगे तो इट इज लाइक Q upon 4 pi R square. इट इज अ कांस्टेंट, इजंट इट? यू सी इट इज अ कांस्टेंट। एक वैल्यू तो आई, पॉइंट ही तो आगे एक तरीके से। अगर ये अंदर भरा होता चार्ज एवरीवेयर इनसाइड, then you can write this charge density to be dependent on some small r. Then you can plot some sort of graph, that is, it is Q upon 4 pi R square or something. Like, are you getting my point? Then you may be able to draw the graph. But otherwise, this is a kind of charge density which is located at a single at a single distance. Radially, it is at a distance capital R. So radially, if you speak, all these all these charges are located equidistant from the center. Is that clear to you? So
yes,
if I just want to make this rho is actually a constant value. So are you getting my point? So this is what it is. So in cylindrical coordinate system, let's say if I want to write a charge per unit length, not charge, because charge we've done already. And let's say it is distributed uniformly on because on a cylindrical surface. Cylindrical surface of, let's say, take radius some different, because small r, then let's say take b. Okay, radius b. So now my charge density, instead of charge, I'm saying find me the charge per unit length. So let's say this is your cylinder. Your entire charge is distributed on the surface. Your entire charge is distributed on the surface. And let's say its length is capital L. And if I want to find what would be the charge density per unit length. So what would be charge density per unit length? Per unit length, whatever charge is located on the surface divided by length L. So divided by length L. Is that clear? So
Yes.
again, I know that my charge is located only on the surface. So radially, if I speak my charge density, I think this is, you are aware that the cylindrical coordinate systems, in cylindrical coordinate system, because I've used rho here, so I'm not using rho here. Basically, at times you'll find that in books, instead of r, you write rho there. But now rho represents your volume charge density, r would represent your radial distance, phi represents your this angle. So this angle, and z represents your height. Okay. So if this is the case, then it obviously I know that this will be some constant Dirac of r minus b, because your entire charge is located on the surface, isn't it? Now, if I want to, if and I already know that if I want to integrate it with respect to d tau, I would get my total charge q. I think I have given it. अच्छा नहीं दे रखा है अपन को lambda दे रखा है ठीक है I will get total charge q, isn't it? Now if I integrate it, I would get what? So rho r, this will be a Dirac of r minus b, and this will be equals to what? R dr d phi, and then this will be dz is equal to q. Is that clear? Now if I integrate this all over, what I would get? I would get simply, this is getting integrated from 0 to 2 pi. There is no phi term, so forget about it. This is dz would integrate from 0 to L. There is no such things, forget about it. And then there will be from 0 to b, a times Dirac of r minus b into r, and then there you have a dr is equals to q. So you have all these things. So if I just divide this L, so I'll get q upon L. So q upon L is 2 pi a integral from 0 to b r Dirac of r minus b dr. Is that clear? And this q upon L you can write as lambda. This is what q upon L, what does it mean? It means charge per length. So 2 pi a, and then you have this, I think r Dirac of r minus b will give you b, and this will be like okay. So there is a problem. Even if you integrate it from, I think not b, but even if you integrate for greater than b also. So entire charge is located inside only. So you can as well take infinity, because at b you have an infinite sort of contribution. So you just take infinite. So permissible limit says what? Your r can vary from 0 to infinite. And even if your r goes from 0 to infinite, the total charge enclosed would remain q only. So it will not be mathematically discrepant. Otherwise, because at b itself you have a singularity. Similarly, you can correct this also. Instead of r, you can take infinite also. Are you getting my point? Because otherwise, at r itself you have a infinite contribution sort of thing. Okay. So for, even if you take, like, this is your total charge. Even if you take radial distance to be greater than r, your entire charge inside that would remain anyway q only. Is that clear to you? Because here you do not have a
Yes.
charge. Here you do not have a charge. Because problem kya aayegi? Whenever you do a Dirac delta integral, you require that between the limits of integration, your Dirac delta function should lie. It should not lie on the boundary itself. So it will create a problem. So therefore, it will be better to take r lying from 0 to infinite, theta lying from, I think, pi to 0, and phi lying from 2 pi to 0. Is that clear? This you are aware ना, मतलब ये चीज तो पता ही है कि for a cylindrical coordinate system, the permissible limits of phi is this, theta is this, and similarly I would take, because I have actually happened to notice this right now, because होगा क्या कि b पे you have this Dirac delta function, so it is like infinitely contributing there. So you better take r lying from 0 to infinity, because even if you take a longer sort of radius, total charge enclosed would remain anyway q only, because here you do not have any charge. Is that clear? So I don't think there is an issue till now. So lambda would come out as 2 pi AP, and lambda would, I can write A then equals to lambda upon 2 pi B. So my charge density now in spherical polar coordinate system can be written as, not sorry, I can write my, what I can write? I can write my rho r, phi, and z as A, which was lambda upon 2 pi B, and then Dirac of r minus. Is that clear? Is that clear to you?
Yes.
Okay. Okay. So what I would do is, these are some of the questions that I've given to you. One question I'm giving you for homework in this particular segment. Try to write what you can say, charge density of total of you cannot say charge Q distributed uniformly or you can say what should I say, over a flat circular disk of negligible thickness. So thickness you forget about it. Negligible thickness and radius capital R. And try to use cylindrical polar coordinates first. Try to use cylindrical because you've done cylindrical polar coordinates. Try to use cylindrical polar coordinates. How to go about it? So if I want to, if I want to express this particular charge density, how would I do? I know my entire charge is distributed over the flat disk and thickness is negligibly small. So I'll not even take thickness, but I'm just showing for right now that not even this, negligibly small. So this distance is almost zero. Forget about it. Let us not even ring, but rings thoda sa, there is motai, thoda sa thickness hai, but that thickness is negligibly small. So forget about this. So overall, if I want to write in cylindrical polar coordinates, this would be my z, this height would be my z, which is actually zero only. So this will be located on z equal to 0. Is that clear? Because my height is negligibly small, so I can expect my z to be 0 when like if I talk about in the cylindrical polar coordinate system would require me 3 things. One, that is z, that is height. Second, that is this radius, and then I should have theta or phi, whatever you say. Is that clear? So my entire charge is over this flat disk. So I'll make it with some other color. So I'm explaining you the problem so that you can arrive at some solution. So my entire charge is distributed on the flat disk now. It is not like it is not on the surface, but on the entire flat disk. Is that clear to you? So this is my entire charge, and which is given by, I think, capital Q. So my capital Q is uniformly spread over this flat disk. Uniformly spread, or you can say uniformly distributed over this. Is that clear? भरत समझ में आ रहा है? कल्पना समझ में आ रहा है?
हाँ भैया।
है ना, थोड़ा सा मतलब ये इस तरह
भैया अगर आप फ्लैट डिस्क बोल रहे हो तो इसको मतलब सिलेंड्रिकल पोलर कोऑर्डिनेट्स में क्यों ले जाने की जरूरत पड़ रही है?
मुझे बात समझ नहीं आ रही, क्या बोल रहे हो? सॉरी,
मतलब आपने कहा ना ये फ्लैट डिस्क सर्कुलर डिस्क ले रहे हैं हम, तो इसको है ना 3 कोऑर्डिनेट सिस्टम में ले जाने की जरूरत क्यों पड़ रही है? मतलब वो मेरे को नहीं समझ में आया।
नहीं 3 डायमेंशन में ले जाने की जरूरत, हाँ मैं मान रहा हूँ तुम्हारी बात। तुम ये कहने की कोशिश कर रहे हो कि इफ देयर इज नेग्लिजिबल थिकनेस देन व्हाई शुड आई नॉट टेक इट एज अ रिंग केस और टेक इट एज अ 2 डायमेंशनल केस एंड नॉट टेक इट एज अ 3 डायमेंशनल केस, राइट? इज दैट सो? सो जनरली जब भी तुम डिस्क बोलते हो तो डिस्क इज जनरली नेग्लिजिबली स्मॉल, मतलब जो उसकी हाइट होगी आप नेग्लिजिबली स्मॉल ही मानोगे। मतलब डिस्क मतलब फ्लैट डिस्क जब भी बोलोगे you will always consider that as a 3 dimensional object, लेकिन thickness negligibly small बोलो, thickness will not consider। मतलब मैं कैसे समझाऊं इस चीज को कि मतलब बहुत ही नेग्लिजिबली स्मॉल होगी तो इसको तो ऑलमोस्ट 3 डायमेंशनल केस ही मानोगे। लिमिटिंग बिहेवियर उसका 2 डायमेंशन जैसा दिख रहा है, मतलब इफ यू आर नॉट कंसीडरिंग एट ऑल द थिकनेस आई कैन अंडरस्टैंड जो तुम कह रहे हो, लेकिन दिस इज हाउ इट इज। सो मतलब समझ पा रहे हो, whenever you are saying that we are discussing a flat disk, it implies that you are discussing almost a 3-dimensional object with a very negligibly small height, so you can actually I'll not neglect that height, I will use some sort of thing, don't worry, like I don't know how to express myself, but this is how it is। मतलब मैं समझ गया what you want to say, दैट अगर रिंग ले लेते तो व्हाट इज रॉन्ग? रिंग में दिक्कत क्या है? रिंग में योर एंटायर चार्ज लाइज ऑन द surface. Surface बोलोगे क्या बोलोगे? On the periphery of the circumference. Disk में entire charge lies on the surface, like on the top of it. And the point is this कि क्योंकि वो negligibly small होता है, you know, तुमने बचपन में पढ़ा होगा sigma upon 2 epsilon naught and sigma upon epsilon naught. इसके फॉर्मूला इजी तो होते हैं तब अगर लिमिटिंग केस में लो तो,
हाँ वो देखो
है ना? चलो I'll explain later on, वो चीज हम बाद में देखेंगे, but overall understand this is a sort of system whose charge density we are interested in right now. Okay, so how to write? So यहाँ पर क्या करो, यहाँ you know that your, यहाँ एक चीज करते हैं ना, यहाँ पे एक और चीज हो गई है. Now you don't your क्या कह सकते हैं your यहाँ पे मैं ऐसा लिखता हूँ इसी चीज को, देख यहाँ पे दिक्कत क्या हो गई है, your charge is completely located from on the disk. So now तुम ये देखो कि your charge is completely on from here to here. मतलब अब ये पूरा डिस्ट्रीब्यूटेड है. पहले क्या था, in other cases what we saw that your entire charge was on the surface, but now your entire charge is lying on the disk itself, on the flat disk itself. Now if you want to write this charge density, you need something other than your what you can say, you need something other than your, you should say Dirac Delta function, because Dirac Delta function would require that your charge is lying at some point, like at some distance. So for example, अभी इससे पहले जो cases किए थे, your entire charge was located on the cylindrical surface. So basically the entire charge was located at a distance r equal to b. Here also you can see your entire charge was located at r equals to capital R. So यहाँ you can use Dirac Delta function. यहाँ पर भी you can use Dirac Delta function in a way that your entire charge is located at z equal to 0. मतलब अगर इसकी thickness negligibly small मान ले, अगर इसकी thickness negligibly small मान ले, जो कि दे भी रखा है क्वेश्चन में, if I consider my thickness to be negligibly small, my entire charge is located at z equal to 0. Is that clear? Like completely flat ही मान ले. Is that clear? ठीक है, completely flat मतलब this is negligibly small, this is negligibly small, and this is तुम ऐसा मान लो जैसे रिंग को अंदर से भर रखा है, and this entire what should I say, मतलब अंदर की तरफ सारा चार्ज भरा हुआ है. अब because the entire charge is inside, so you can use something called as your unit step function or heaviside function. I taught you all these unit step function we have already done. So if you want to write heaviside function or simply your क्या कह सकते हैं heaviside function, or you say your unit step function, what does it mean? It means that for all r less than r you will have 1, and for all r greater than r you will have 0. Is that clear? So you know that for all r greater than r you do not have any charge, but for all r less than r you have a charge. So it will somehow, given a constant, it will somehow make some sort of sense. Is that clear? मतलब हम क्या कहने की कोशिश करें, हमें कह रहे हैं कि हमारा जो चार्ज है वो entirely अब inside है. It is not only on a point but entirely inside भी है. Basically क्या कहने की कोशिश कर रहे हैं, at r equals to, at r less than r your entire charge is located. Is that clear? And r greater than r you do not have a charge. So there would be some no doubt term of unit step function also, and there would be some constant. Is that clear?
Yes, sir.
Is that clear now? Okay. Now what I would do is, see your z, if I take below or if I take above, in short, z lies from minus infinity to plus infinity. It can vary from minus infinity to plus infinity. My phi can vary from 0 to 2 pi. And my r can vary from 0 to infinity. So in cylindrical polar coordinate system, your r can vary from 0 to infinity. Your z can vary from negative infinity to positive infinity, whatsoever suits you. And your phi can vary from 0 to 2 pi. Is that clear? So this is typically in a cylindrical polar coordinate system, you can have these sorts of limits on your individual coordinates, that is r, phi, and z. So if I integrate all over, I know that even if I integrate all over, this would give me Q only. This entire charge, in any case, I will get the entire charge Q only, because even if I make a large like a cylindrical polar coordinate system here, and if I integrate on the entire space enclosing this particular body, total charge inside would remain Q only. So total charge will be rho r d phi d tau would be minus infinity to plus infinity. You have Dirac z dz minus, sorry, 0 to infinity, your h r minus capital R dr, r also is there, and then you have from 0 to, what was there, uh, sorry, 0 to 2 pi, you had this your phi, and then you had this a, and then you had this total q. Is that clear? बात समझ पाए? रो phi dz, अगर इसको मतलब अगर if you enclose this particular system in the entire cylindrical periphery, where your z varies from minus infinity to plus infinity, your phi varies from 0 to pi, and your r varies from 0 to infinity also, total charge enclosed in any case would remain capital Q, because you do not have charge here, so total charge will remain Q only. Is that clear to you? And why am I doing this? Because otherwise, if I integrate from 0 to infinity, there would be a problem, because so therefore I'm just using the entire limits for the entire coordinate system. So if I use those limits, what I would get is a, this will be 1, I think. This will be 5, I think. I have to think about this. From 0 to infinity, I know my this particular thing is 1. Because here for all r greater than r, you have, for all r greater than r, you have 0. So I will write from 0 to r, you have r into 1 dr is equal to Q. Is that clear? And if I solve it, I will get a is equal to q upon, this will give you r square by 2, 2 so 2 cancel, so it will give you q upon pi capital r square. Is that clear? So if I want to write the volume charge density for a negligibly small flat disk, negligibly small thick, negligibly flat disk of negligible thickness, na? Flat disk of negligible thickness, then the volume charge density will be given by Q upon pi r square, Dirac of z, and you can write some theta function. Oh, sorry, I have written Heaviside function r minus capital. So this is how you are going to write your volume charge density when, like, छोटे बचपन में तो ठीक था, चल रही थी गाड़ी Q upon pi r square से. But now if somebody asks you what would be the volume charge density, this will be an appropriate description of the volume charge density in cylindrical polar coordinate system. Is that clear?
Yes, sir.
थोड़ा सा difficult है, but मैं क्या कर सकता हूँ? The only problem of our life is that we've grown old and we are getting all the more complicated. So enough of innocence in dealing with things, enough of innocence in dealing with subject also. So अब कुछ नहीं हो सकता. ठीक है? Are you getting my point till now? And so and also I should refer it. I mean, where I have got this particular thing and where I teach this particular section from, so that you people are also going to be teachers someday. So this is from Jackson. Okay, so this treatment is from Jackson Excel. So that is what I'm saying. Okay, is that clear? I know everybody is aware of the book called as Jackson. If you're not aware, kindly see the book called as Classical Electrodynamics. Its Indian edition
Yes,
is right now flooding all over, like it's now very costly. But overall, Jackson is considered to be the postgraduate text for all the Indian students. And undergraduate text is Griffith. So both of them, if you study, तो अच्छा ही रहेगा overall. ठीक है? Now, certain fields I'm going to discuss, which I was discussing yesterday also, but somehow I messed them up. So, certain electric fields. Okay, so if I have an electric field which is given by, if I have an electric field in the space given by, what I wrote yesterday was a e to the power minus br. Actually, I wrote wrong. Actually, I thought I would be remembering that quite fondly, but overall, I was wrong. Did not do it. Okay. So it was like a e to the power minus br upon r square r cap. So if this is your electric field, at times you'll find question being asked that what would be the charge distribution. What would be the charge distribution giving rise to such kind of electric field in the space? Giving rise to such kind of electric field in space. So if I talk what kind of charge distribution can give rise to such a field? अच्छा okay, एक और चीज I would explain. देखो अगर मान लो if at all these questions come in the exam, ना मान लेते हैं if these questions come in the exam, so exam wise I am telling you what is the strategy, integrate them and find Q किससे आ रहा है. Are you getting my point? मतलब if there is some inconsistency you will never get Q. So what is the best strategy in the examination? If at all तुम्हें ऐसा लग रहा है you are not able to construct such kind of volume distributions or charge distributions, what you can do in exam, you can just try to integrate reverse. So for example, you will get some question and there will be some options. Let's say there are 4 options. Just try to integrate all those 4 options. From whichever 4 option you get charge capital Q or what total charge Q, whatever is given in the examination, just take that and come back. So these are all the ये सारी चीजें वो कौन सी हैं जो मैं एक रूम में बैठ के आराम से with all premeditated thought में कर सकता हूँ. But in examination हो सकता है I could not even think what is going. So it's better कि in examination, if you are facing some examination, mostly I expect such problems to be asked in JEST or TFR. But Bharat says that these days net examination has also become equally difficult, so I can expect that in net examination also. So overall, the idea in examination would be to integrate them back to get charge Q. Is that clear? Okay, so now what is if certain electric field is given, so you should remember that we wrote that del dot r cap upon r square. So for example, divergence of this vector field was equals to 4 pi Dirac cube of r. This is what we know from our initial discussions on Dirac delta function. And also there is a vector identity which suggests that if I want to find the divergence of u v vector, where u is a scalar, v vector is a vector, it will give me I think u divergence of v vector plus grad u dot grad u dot v vector. Is that clear? So
Yes.
how to remember this particular formula? The only way to remember this particular formula is to see how can we make what all scalar that we can extract from this. So what all scalars we can do? We can take a divergence of v vector and then multiply with u, fine. And then we can take grad of u and dot product with v vector. These are the 2 possibilities that we have in our hands. And this is how this vector identity can be remembered. I'm not saying to derive it, but remember this particular vector identity. Is that clear? And we already know that my integral Dirac cube r d tau is equals to 1 on the entire space. These 3 things needs to be remembered before attempting such questions. So in these questions, what happened? If you encounter these questions in examination, you simply take a divergence. There will be a flaw that you cannot retract back, at least in examination conditions. So what you do, you just cleverly take this r cap upon r squared. Thoda sa, you'll have to make certain kind of manipulation. What I'll do, I'll certainly take this r cap upon r square aside. So keep this aside, because we already know that this can form a Dirac delta function. So this can form a Dirac delta function. Otherwise, there will be a difficult treatment to this, and probably I have a less time to explain all those things. But overall, let us do what we know till now. So what I would do, I would simply take del dot e vector, and del dot e vector no doubt would give me rho as a function of r. And what does what it will give me is simply del dot. I have this a, forget about this a, e ki power minus br, and then you have r cap upon r square is equals to what? It will give me rho as a function of r upon epsilon naught. Is that clear? And what I will get is, I will simply get this. I'll take this a as a constant. So keep that a as a constant. Okay. Keep that a as a constant. And you take a grad of e ki power minus br, which will be minus b e ki power minus br r cap dot r cap upon r square, and then plus e ki power minus br and del dot r cap upon r square. It will give you rho as a function of r, and it will be equals to some epsilon naught into a, and this is it. So what you will get rho as a function of r as, I think, minus, if I'm not wrong, epsilon naught A B upon R square e की power minus BR. And then you have plus, I think this is 4 pi Dirac cube R, and then you have e की power minus BR. Is that clear? Okay, so what does it suggest? It suggests that there is a strong positive charge at the center. So there's a positive charge at the center. You can see that 4 pi, and there would be some A also, sorry. So there's a strong positive charge at the center, not this. E की power minus BR would be there. Okay, e की power minus BR would be there. So, and see, this Dirac cube R, what does it suggest? It is equals to some infinite contribution at R equal to 0. And if it is not R equal to 0, then it will be 0. So overall, this particular thing is valid only for R equal to 0, because if R is not equal to 0, this entire thing would become, overall would become 0. So at times you'll find books taking this liberty of making it e की power 0. Are you getting my point? So see, if it remains there, that then also there is a no problem. But even if it, see, for example, what I want to suggest is, if you want to integrate, say, let's say if I integrate rho R d tau. So if I integrate this stuff, I know that only at R equal to 0, it makes some sense, because at R not equal to 0, it would be 0. So overall, this term would remain only valid for R equal to 0. So at times, in order to better express your answer, what people do, they simply write it as 4 pi epsilon naught A Dirac cube R. Is that clear? Simply this. They will not even write e की power minus BR, because, see, again, I'm telling you, this Dirac delta function is equal to some non-zero value only if it R is equal to 0. R not equal to 0, it will be 0. So e की power minus BR, even if it accompanies my Dirac delta function, it would hardly matter, because it will be like e की power minus 0 only. Is that clear to you? So at times you'll find such expressions in books. Don't worry about it. So what does it represent? It represents your point charge, positive point charge lying at the center and surrounded by an exponentially decaying negative charge density. Exponentially decaying negative charge density. So we'll catch in the next. We'll catch on this topic in the next density.